All right, so we are going to be talking right now about big O notation. It's come up a couple of times. So just kind of off the top of your head, what do people know about big O notation?
It's the absolute worst time your program can run, I think.
So it's a representation of the absolute worst amount of time your program can run, or the most amount of time your program takes to complete.
Yeah, like the worst case scenario.
And I guess it's also about the correlation between the growth of your algorithm, or let's say the size of your data set in relation to how quickly the runtime grows.
Yeah, so what he said was the correlation between the size of your data set or the input and how long it takes your code to run. Anyone else have another definition they'd like to share? Okay, so we're going to do this quick presentation about big O. So we've got this benchmarking resources here. I'm actually going to move this over a bit. So we have a cool little thing about, it's just a comparison of different sorting algorithms. Again, it's just, visualization of how long different things take to run, and you can see some algorithms take longer, some algorithms take shorter. Considering the fact that all of the data sets for each of these are the same size. So all of these are taking cool music, I'm getting into it. All of these take input of size n, but they don't all run the same amount of time. So this is essentially the stakes of what we're talking about when we're talking about big O, is we want something that runs quickly as opposed to something like selection sort or cocktail sort, which is taking for bloody ever. Oops. So there's also a website we can go to called highperformance.readthedocs.io, which is documentation for benchmarking. The slide deck is also on GitHub if you want to take a look at this in more detail, but this is essentially documentation for how you can kind of better understand the speed of your own code when you're running it. All right, so this may sound like a silly question, but why do we want our code to run fast?
Because faster is always better.
Faster is better. Why is faster better?
Time is money.
Time is money.
Sometimes literally.
Yeah.
Like allocation of resources.
Allocation of resources, meaning the allocations of memory, things like that.
Like in web development, studies have shown that if your page doesn't load quite fast enough, then you actually you experience a significant drop in customer engagement.
Yep. So if your website loads slowly, you're going to your customer engagement's going to wear off. People are just going to go someplace else because it takes forever for your site to load. So big O notation right now, it may seem a little weird to think about because right now our code operates at a very, very small scale, and the only person it really impacts is yourself and maybe your paired partner. But later on, your code is going to be impacting the experience of thousands of users. And since every piece of code you write is probably going to be reliant on another, then you want to make sure that every piece of code runs quickly so that nothing gets slowed down. So big O is the complexity of your function, is the O. In terms of input size, the N. So essentially, it's how long it takes to run and how complex is it. And big O typically takes a couple of forms, which we can kind of see here. So O of 1, the speed doesn't depend on the size of the data set. So no matter how big the piece of data you give it, it'll always run at exactly the same speed. Can anyone think of a scenario where this could happen?
Accessing a key value pair in a dictionary.
Yeah.
That's all.
Yeah, accessing a key value pair in a dictionary. It doesn't matter how big the dictionary is, as long as we have the key, we have the value. So therefore, we have an O of 1. good example. An O of log n, so that means you can get 10 times more data, but only 2 times more time. Someone better at math than me can tell you what log means again. But
Log is the amount of, it's basically how to raise the number to the power of something.
Mhm.
So like, in base 10, you'll go like, it's.
all right. I think, yeah, a log might be an entire other lecture, which isn't super relevant to Big O specifically. But if you see O log n, that's still pretty good. It just means that if you give it 10 times, like 10 times of the data, you only increase it 2 times, which is good. O of n means 10 times the data means 10 times more time. It's the line just goes in a straight diagonal thing. So a pretty basic example of something with an O of n would be you have an array of size n, and you loop through the entire array. So therefore, the complexity of the code is dependent on the size of the array. The bigger the array, the longer it takes. Then we have O n log n. 10 times the data means 20 times more time. I'm not entirely sure what would be an example of code that runs in that particular way. But then we have O of n squared. 10 times the data takes 100 times more time. We've seen a few scenarios where we might have something with an O of n squared. What gives us an O of n squared? Yeah, nested loops. Nested loops give you an O of n squared because you got to loop through it and you got to loop through it again inside of that loop, and it increases exponentially. And if you have an O of 2 to the nth power, you screwed up big time. The lithium crystals are breaking up. So you want to keep your code as close to the top of this chart as possible. And sometimes it's unavoidable. You're going to have sometimes you just have to loop through something. Sometimes you can't avoid a nested loop. But if at all possible, keep the complexity down.
Is there a list of which method types fall under which?
There probably is. I do not have one, but I'm sure we could find one if we looked for it. Okay, so kind of more detail. So O1, constant time. Amount of time it takes to run your code is constant. Whether you pass it on 1 argument or a million arguments, all the same. So the example they give us here is the first element is red. So return true if array 0 equals red, else false. So it doesn't matter the size of the array because we're only checking one thing of the array. The real life example is a pigeon race versus internet speeds. Has anyone ever heard this story of the pigeon race versus the internet? You have?
Yeah. So it was the time when they tried to transmit data, right? And they compared.
Okay.
They compared how fast they could transfer a certain amount of data versus like attaching it to a pigeon and just letting it fly.
Mm-hmm.
Right?
Yeah, exactly. So a couple decades back, there we go. They decided to have a race to see who could transmit data the fastest, the internet or a carrier pigeon. And under certain circumstances, the carrier pigeon won. And the reason for that is the more data you have to transfer, the more time it takes if you're using the internet. So a huge amount of data by computer standards could take quite a long time. A carrier pigeon will always take the same amount of time so long as that data fits in the little thing around their leg. So a carrier pigeon is an example of something with a O of n, of O of 1. It doesn't matter what data you give it, it'll always go the same speed. All right, O of n is linear time. Runtime will grow linearly based on what you pass in. So for example, this loop, which is we're looking for a value in an array. So real life example, mo money, mo problems. So I don't think that's a real life example, but it does demonstrate the concept pretty well. The more you give it, the more complex it'll be. So an array of 5 items won't take very long at all, but an array of 10,000 items might take significantly longer. quadratic time, O of n squared. So the example they give us here, all combinations in an array. So we're looping through an array twice and appending every combination of things in the array. So in this particular case, we have a for loop checking every single number. And every time we go through that loop, we go through the entire loop again in that inner loop. And because of that, the larger the loop, it just increases quadratically. So again, 5 items, not so bad. 10 items, not so bad. 10,000 items, your computer might hang up for a while. It'll double. So key takeaways about Big O. Searches through hashes are faster than searches through arrays because hashes don't keep track of indices. You can just access the thing you want directly. Whenever possible, avoid nested loops, loops within loops. Sometimes it doesn't mean that you can never do them, but if there's ever an alternative, you should probably do that. And if you find yourself writing code that is poor Big O complexity, consider refactoring. Any questions about Big O?
One, I do remember reading that if you have the program do a for loop versus writing out the for loop was usually faster.
When you say writing out the for loop, what do you mean?
I was trying to think of the name of it, but I'm drawing a blank. So if you do, say in JavaScript, for I equals 0, I is less than whatever, I plus plus, versus just the command line that tells it to search for it on its own, which is basically still doing the loop. JavaScript figuring out the loop on its own was slower than writing out the for I equals 0. What's that?
You're going to say using like a built-in method versus writing out for you?
Yeah.
So it's writing out, which one was faster in this case? Writing out
the
was faster?
Ran faster, yeah.
Yes. So when you use, there are some methods that kind of do they essentially loop over a method for you. We're actually going to be talking about some of those methods later today. And those have their own Big O complexity, even though we don't see it. So even though it's just one line of code, it is still looping through the code. And so in many cases, if you want to increase performance, yes, manually writing out the for loop, like in JavaScript using the for I equals 0, I is less than n, I plus plus, that does improve performance a bit. Cool. So one thing I do want to talk about real quick that isn't really mentioned in the slides is Big O complexity. These are really the only notations you'll ever see. Oops, wrong one. These are the only notations you'll ever really see. 1, n, n squared, and n log n, 2 to the power of n. You won't see something like 2n, 2 times n, or 3 times n, or n divided by 2, because that's not really, in most cases, multiplication and division doesn't really affect the performance speed enough to really be statistically important. So even if you're saying, you have a while loop based on the size of an array, but the while loop goes 2 times the size of the array, it's still based directly on the size of your array. It's not going to it's not going to be 2 times the size of the array. So these are really the only Big O notations you'll see. And yeah, Big O comes up a lot in code reviews and coding challenges and whiteboarding challenges. Actually, John asked me about Big O notation when I was interviewing for this job, and I had completely forgotten about it because it had been a while since I'd actually thought about it. But, kind of going back to what John was saying yesterday, if you don't know something, be honest. So that's what I did. But yeah, Big O notation is something you should be thinking about. It's not necessarily something that you need to say, like every time you write a program, write out what the Big O complexity is at every time. Just keep it in mind so that you are keeping your code optimal and understanding what's really going on in the background there. All right, cool. Any other questions?
I just want to say that this is a pretty complicated topic, so it's okay to be kind of, lost, because people take a semester or 2 semesters worth of college courses, so, like, this is difficult stuff.
Yeah. So you're saying is Big O is much more complex than I'm presenting it here. There are entire fields of study dedicated to figuring out just how code runs and how to make it more optimal. So I think for our purposes, understanding it at this level is enough. If you're interested in learning more, feel free to do some research on your own and report back to us, because I think we would love to hear it and your classmates would love to hear it. Okay, cool. All right, so let's see here. Kelly should be coming in at 9. So let's take an 8-minute break. Everybody be back here by 8:59 so that you're ready for her presentation. And thank you.
Just avoid recursion, right?
Yeah, and avoid recursion. Recursion is bad.
I moved to Texas.